Somewhere in the depths of the cosmos, two colossal black holes spiral toward each other in a lethal dance. Their immense gravity warps space itself, sending ripples through the very fabric of reality. Ripples so powerful they stretch and squeeze everything in their path, even light. This isn't science fiction. It's one of the most violent events in the universe, and it happened over 1 billion years ago. But the echoes of that collision, the gravitational waves it unleashed, traveled across the cosmos until they finally reached us, a faint whisper from the abyss, captured for the first time in human history. Gravitational waves are the universe's way of shaking the cosmic table, and today, we're diving into 30 astonishing facts about these extreme disturbances in spacetime. From the moments they were first detected to the mind-bending ways they twist reality, these waves aren't just scientific curiosities, they're keys to unlocking some of the biggest mysteries of existence. Think about it, every time a massive star collapses or black holes merge, they send out these invisible signals carrying secrets about the birth of galaxies, the nature of gravity, and even the origins of the universe itself. What makes gravitational waves so extraordinary isn't just their power, it's what they reveal. They let us observe the universe in a way light never could, peering into the darkest corners where telescopes fail. Imagine listening to the cosmos instead of just looking at it, hearing the crashes and collisions that shape everything we know, and the wildest part. These waves are passing through you right now, stretching and compressing space on scales so tiny we once thought they'd be impossible to detect. But humanity did detect them because even the faintest whisper from the universe, if we listen carefully enough, can change everything we think we know. Buckle up, because we're about to journey into the heart of spacetime's most extreme distortions, where black holes scream, neutron stars ring like bells, and the universe itself bends to the rhythm of gravity's song. The moment that changed astronomy forever happened on September 14, 2015, when scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, caught something extraordinary, a wobble in spacetime so subtle it shifted their detectors by less than 1,000th the width of a proton. This faint tremor wasn't random noise, it was the death cry of two black holes, each around 30 times the mass of our Sun, locked in a final, furious embrace 1.3 billion light-years away. Their collision was so violent it unleashed more energy in a fraction of a second than all the stars in the observable universe combined, warping the fabric of reality itself. And yet, by the time those ripples reached Earth, they were weaker than a whisper, so faint that even Einstein, who predicted their existence a century earlier, doubted we'd ever detect them. But LIGO laser beams, bouncing down 4-kilometer-long tunnels in perfect harmony, caught that infinitesimal stretch and squeeze of space. The detection wasn't just a triumph of engineering, it was proof that the universe speaks in gravity as well as light. For the first time, we weren't just seeing the cosmos, we were hearing it. Think about that, those black holes collided before multicellular life existed on Earth, and their gravitational waves traveled through eons of cosmic history just to tell us their story. And what a story it was, confirming Einstein's theory of general relativity in the most dramatic way possible while unlocking an entirely new way to explore the universe. Before this discovery, astronomy was like watching a silent movie. Now we've plugged in the speakers. Those waves revealed details no telescope could, like the black hole's masses, their spin rates, even the final milliseconds before they merged into one. It's like listening to a drum beat in the dark and knowing exactly how big the drum is, what it's made of, and how hard it was struck, and this was just the beginning. Since that first detection, gravitational waves have exposed neutron stars ripping each other apart, hinted at mysterious objects we can't yet explain, and even given us clues about the universe's expansion rate. All because 100 years ago, a brilliant physicist scribbled equations on a chalkboard, and a team of stubborn scientists refused to stop listening for echoes in the void. So what exactly are these cosmic ripples that shook the foundations of physics? Picture spacetime not as an empty stage where cosmic events play out, but as a living, breathing fabric, a stretchy sheet that bends, warps, and vibrates under the weight of massive objects. Just like dropping a bowling ball onto a trampoline sends ripples racing outward, when colossal objects like black holes or neutron stars accelerate, whether by orbiting each other or colliding, they create distortions that surge through spacetime itself. These aren't just abstract wrinkles, they're actual waves traveling outward at the speed of light, compressing space in one direction while stretching it in another. Here's where it gets wild. Unlike light, which can be blocked or scattered, gravitational waves pass through everything: planets, stars, even you, unimpeded. Imagine shouting into a pillow. Sound gets muffled, but gravitational waves are like a shout that pierces through every obstacle in the universe without fading. That's why they're revolutionary. They carry information from events no telescope could ever see, like black holes merging in pitch-black voids where no light escapes. And just like ocean waves have crests and troughs, gravitational waves alternate between squeezing and stretching space in a rhythmic dance. If you were floating near two colliding black holes, you wouldn't just see the chaos, you'd feel it. Your body would subtly distort, first squished horizontally while stretched vertically, then reversed over and over as the waves passed through you. Of course, the effect is so infinitesimal on human scales that we'd never notice without instruments sensitive enough to detect shifts 1,000 times smaller than an atomic nucleus. This is why Einstein's theory was so brilliant, and why proving it took a century. He realized gravity isn't just a force pulling objects together. It's the curvature of spacetime itself, and when massive objects move violently, they create these propagating ripples. It's as if the universe has its own language of warps and vibrations, and we've only just learned to decode its first words. Every detection since that first black hole collision has been like tuning our ears to a cosmic symphony, one where the instruments are the most extreme objects in existence, playing a song written in the fabric of reality. On August 17, 2017, the universe delivered a spectacle so dazzling it rewrote astrophysics overnight. Far beyond our galaxy, two neutron stars, cosmic corpses so dense a teaspoon of their material would weigh 1 billion tons, finally succumbed to gravity's pull after a death spiral lasting millions of years. Their collision, dubbed GW170817, didn't just send gravitational waves rippling through space-time. It unleashed a fireworks show visible across the electromagnetic spectrum, from gamma rays to visible light, confirming something scientists had only theorized. Neutron star mergers are cosmic forges where elements like gold, platinum, and uranium are born. This event wasn't just loud, it was deafening. While black hole mergers are like deep bass notes in the cosmic symphony, neutron stars crash with a higher pitched clang, ringing spacetime like a bell. The gravitational waves from GW170817 traveled 130 million light-years to reach Earth, but the real astonishment came when telescopes swiveled to the spot LIGO detectors pinpointed. There, in a galaxy called NGC 4993, a Kilonova explosion blazed with the brightness of 1,000 supernova, its light laced with the spectral fingerprints of freshly minted heavy elements. Here's why this matters. For decades, we couldn't explain where half the universe's gold came from. Ordinary supernova couldn't produce it, but neutron star collisions. They're perfect alchemical labs. When these ultra-dense objects collide, they eject material at near light speed, creating conditions so extreme protons and neutrons are smashed together into atomic nuclei heavier than iron. The Kilonova's afterglow revealed telltale streaks of strontium and cesium, proving these mergers are cosmic jewelry stores scattering precious metals across the cosmos. But GW170817's true triumph was its role as a Rosetta Stone for multi-messenger astronomy. For the first time, we didn't just detect gravitational waves, we saw and heard the event, combining data from LIGO, gamma-ray satellites, and optical telescopes to reconstruct the entire cataclysm. The gamma-ray burst arrived just 1.7 seconds after the gravitational waves, moving at light speed like a synchronized cosmic telegram. Meanwhile, the Kilonova's glow lingered for days, allowing astronomers to study the aftermath in unprecedented detail. This collision did more than solve a mystery. It revealed how interconnected the universe truly is. Every gold ring on Earth likely contains atoms forged in a neutron star collision older than our solar system, meaning your jewelry isn't just metal, it's stardust from one of the most violent events in existence. And with each new detection, we're learning these mergers aren't rare. They might be happening every few minutes somewhere in the universe, seeding galaxies with the elements that make planets and life possible. GW 170817 wasn't just a scientific milestone. It was a humbling reminder that we're literally made from the echoes of cosmic catastrophes. One of the strangest sounds in the universe isn't a sound at all. It's a ripple in space-time turned into something we can hear. When two black holes spiral toward collision, they don't just warp space silently. They create a rising tone scientists call a chirp, a ghostly frequency shift that starts low and surges higher as the black holes whip around each other faster and faster, like a cosmic mosquito speeding toward its doom. Here's how it works. Imagine swinging a squeaky toy in circles above your head. The faster you spin it, the higher the pitch rises. That's the Doppler effect in action. Now replace the toy with black holes, each weighing dozens of suns, spinning at half the speed of light before smashing together. Their gravitational waves don't just ripple outward, they shift in frequency as the orbit tightens, stretching and squeezing space-time in an accelerating rhythm. The chirp might last mere seconds, but it tells an entire story. The initial low hum reveals how far apart the black holes began. The rising pitch exposes their accelerating dance, and the abrupt cutoff, that final, silent moment, marks the instant they merge into one. This isn't just theoretical. LIGO detectors have captured it multiple times, translating space-time vibrations into audible sound. What's haunting is what the chirp hides. That final silence isn't just the end. It's the birth of a new black hole, ringing like a struck bell as it settles into its final form. Scientists call these vibrations quasi-normal modes, and they reveal the newborn black hole's mass, spin, and even whether Einstein's equations hold true in these extreme conditions. The chirp is more than data, it's proof that the universe has a voice. Before LIGO, we could only see black holes through their effects on nearby stars. Now we can hear them die. Every chirp is a death certificate written in gravity, a fleeting signal from a pair of invisible monsters that shook the cosmos long before life crawled onto land. And the wildest part, these sounds are all around us, passing through Earth constantly, a symphony of collisions we're only now learning to hear. Gravitational waves don't just bend space, they twist time itself. Imagine standing near a collision so violent it warps the fabric of reality. As the waves pass through you, your watch wouldn't just tick differently, it would literally speed up and slow down in sync with the ripples. This isn't science fiction. Atomic clocks aboard GPS satellites already account for these subtle distortions, proving time is far more fluid than we ever realized. Here's how it works. Einstein predicted that massive objects don't just curve space, they drag time along with them like a heavy ball sinking into a trampoline. When gravitational waves ripple outward, they create alternating zones where time stretches and compresses. If two ultra-precise clocks were placed a few kilometers apart, a passing wave would momentarily make one run faster than the other, by less than a billionth of a second, but enough for modern instruments to detect. GPS satellites orbiting 12,000 miles above Earth rely on atomic clocks accurate to within a billionth of a second per day. But Earth's gravity weakens slightly at that altitude, meaning time actually moves faster up there compared to the surface, an effect called gravitational time dilation. Without correcting for this, GPS coordinates would drift by nearly 7 miles per day. Now add gravitational waves. When these cosmic ripples pass through, they tweak the satellite clock's timing ever so slightly, like an invisible hand adjusting the universe's metronome. The wildest part, these time warps aren't rare. Every black hole merger, every neutron star collision sends out waves that briefly alter time's flow across the cosmos. You've never noticed because the effect is vanishingly small on human scales, but for a split second during the merger of two black holes, time near the event stretches like taffy before snapping back. It's as if the universe itself breathes, its heartbeat measured in distortions of spacetime. This revelation changes how we perceive time. We think of it as a steady river, but gravitational waves prove it's more like a choppy sea, surging and receding under the influence of cosmic violence. Those GPS corrections, they're not just engineering feats, they're proof we're learning to navigate a universe where time is as malleable as clay, shaped by the very collisions we're now beginning to hear. Some 7 billion years ago, when the universe was barely half its current age and our solar system didn't even exist, two cosmic titans engaged in a battle so colossal it defies imagination. Designated GW190521, this gravitational wave carried the signature of the most massive black hole merger ever recorded, a pair weighing 85 and 66 times the mass of our Sun, respectively. Their collision unleashed a shockwave so powerful it distorted spacetime across galaxies, sending ripples that traveled for eons before finally brushing past Earth in May 2019. To grasp how ancient this event was, consider this: when those black holes spiraled into each other, the Milky Way was still assembling itself. The universe was younger, hotter, and far more chaotic, with stars forming at rates 10 times faster than today. Galaxies collided frequently, their supermassive black holes feeding on gas and dust in a primordial frenzy. And in that maelstrom, two heavyweight black holes, possibly born from the direct collapse of giant gas clouds in the early universe, found each other. What followed wasn't just a merger, it was the birth of an intermediate mass black hole weighing a staggering 142 solar masses, a rarity that challenged our understanding of how black holes grow. Detecting GW190521 was like uncovering a fossil from the cosmic dark ages. Unlike the neutron star collision that lit up telescopes, this event left no flash in the sky, just a deep, thundering ripple in spacetime's fabric, lasting barely a tenth of a second. Yet that fleeting signal revealed secrets that light could never convey. The black hole's enormous sizes hinted at a mysterious formation path, possibly bypassing the usual stellar explosion cycle. Their merger also emitted energy equivalent to 8 solar masses vanishing into pure gravitational waves, a conversion so efficient it briefly outshone every star in the observable universe combined. But the true wonder lies in the journey those waves took. For 7 billion years, they traversed an expanding universe, stretching as space itself stretched, carrying a snapshot of a time when the cosmos looked utterly alien. By the time they reached us, the universe had cooled, galaxies had settled, and life had emerged on at least one small planet, a planet whose scientists, against all odds, built machines sensitive enough to catch that ancient whisper. GW190521 isn't just a record-breaking detection. It's a time capsule from an era when the universe was wild, uncharted, and brimming with violence we're only beginning to comprehend. The aftermath of a gravitational wave isn't just a fleeting ripple, it might leave behind a cosmic tattoo etched into spacetime itself. Known as gravitational wave memory, this phenomenon suggests that when violent events like black hole mergers send shockwaves across the universe, they don't just pass through and vanish. Like footprints pressed into wet sand, these waves could permanently stretch and squeeze the fabric of reality, leaving scars that linger long after the collision's echo fades. Think of it this way: when you drag your hand through a still pond, the waves eventually settle, but the water level is forever changed where your fingers passed. Similarly, gravitational waves from cataclysmic events might leave spacetime subtly offset, not just warped temporarily, but permanently dented in ways we're only beginning to understand. This isn't just theoretical. Einstein's equations hint that these memory effects should exist, but they're so infinitesimal that even LIGO precision hasn't caught them yet. Future detectors like the planned Laser Interferometer Space Antenna, or LISA, could change that. Imagine floating 3 spacecraft millions of kilometers apart, linked by lasers sensitive enough to spot a spacetime dent smaller than an atom over that vast distance. Such a system might finally detect memory's faint signature, a permanent shift in the distance between the probes after a gravitational wave passes, like a cosmic ruler that's been stretched and never quite snaps back. What's mind-bending is what this memory could reveal. Unlike the transient chirp of a black hole collision, memory would serve as a fossil record of ancient cosmic violence. By studying these imprints, we might reconstruct mergers that happened billions of years ago, tracing how black holes grew when the universe was young. Some theories even suggest memory could expose hidden dimensions or test whether gravity behaves differently over cosmic timescales. And here's the kicker: if memory is real, then right now, you're swimming in a sea of spacetime scars from collisions older than Earth. Every black hole merger, every neutron star crash has left its mark on the universe's fabric, a tapestry of distortions woven by the most violent events in history. Future astronomers might decode these scars like tree rings, reading the universe's violent past in the permanent wrinkles of spacetime itself. In the cosmic dance of black holes, some partners are stranger than others. Take GW190814, a gravitational wave detection that left scientists scratching their heads. On August 14, 2019, LIGO and Virgo observatories caught the signal of a black hole 23 times the mass of our Sun merging with something puzzling, a compact object just 2.6 times the Sun's mass. That might not sound extreme until you realize this lightweight companion defies all expectations. It's either the heaviest neutron star ever found or the lightest black hole discovered, an awkward in-between object that shouldn't exist according to conventional astrophysics. Neutron stars, those ultra-dense remnants of exploded stars, typically max out around 2.2 solar masses before collapsing into black holes. Yet here was something pushing that limit, refusing to fit neatly into either category. The alternative, a so-called intermediate mass black hole, a hypothetical missing link between stellar mass black holes and the supermassive giants lurking in galactic centers. If confirmed, this 2.6 solar mass mystery would be the first of its kind ever observed, a cosmic Goldilocks object neither too small nor too large, but just right to rewrite our understanding of how black holes form. The collision itself was a David and Goliath affair. The larger black hole's immense gravity stretched its smaller companion apart long before impact, possibly triggering a brief burst of light that telescopes failed to catch. What makes GW190814 so tantalizing isn't just the odd couple involved, it's the window into a shadowy population of black holes we never knew existed. Most black holes we've detected fall into two groups: those under 20 solar masses formed from collapsing stars, and supermassive ones millions of times heavier. The gap between them has been a glaring mystery, with few confirmed sightings of black holes in the middle range. One theory suggests these intermediate black holes could be primordial, born not from dying stars but from the direct collapse of dense gas clouds in the early universe. Others propose they're grown through repeated mergers, like cosmic snowballs gathering mass over eons. Whatever their origin, their existence would solve a persistent riddle: how supermassive black holes got so big so fast in the universe's youth. If middling black holes were common in the cosmos adolescence, they could have served as seeds for the giants we see today. GW190814's smaller object might be a Rosetta Stone for this hidden class. If it's a neutron star, it challenges our models of how dense matter behaves under extreme pressure. If it's a black hole, it hints at a whole zoo of overlooked objects lurking in the dark. Future detections will tell, but one thing's certain: the universe keeps tossing curveballs that force us to rethink the rulebook. Every mysterious signal like this isn't just a detection. It's a dare to imagine the cosmos as stranger and more wonderful than we ever believed. Some black holes don't just move, they whirl with such ferocious speed that they twist the fabric of spacetime into a swirling vortex, dragging everything nearby into their dizzying spin. Imagine a cosmic figure skater pulling their arms in, spinning faster until the air around them distorts, except this skater is a black hole weighing dozens of suns, rotating at nearly the speed of light. These extreme spinners aren't just theoretical oddities. They're some of the most dynamic objects LIGO has ever detected, their furious rotations leaving unmistakable fingerprints in the gravitational waves they emit. When black holes orbit each other before merging, their individual spins act like cosmic gyroscopes, each one tilting and twisting spacetime around it. The faster they spin, the more dramatically they warp their surroundings, an effect called frame dragging. Picture stirring a spoon in thick honey. The spoon drags the honey around with it. Now replace the spoon with a black hole spinning 1,000 times per second, and the honey with spacetime itself. This distortion isn't just a quirk, it alters how the black holes spiral toward collision, imprinting telltale wobbles in their gravitational wave signals. LIGO detectors can read these subtle patterns like a fingerprint, revealing not just the black hole's masses but how fast they were spinning before they merged. The numbers are staggering. Some black holes clock in spinning at over 90% of light speed, a velocity so extreme it flirts with the universe's ultimate speed limit. At that pace, time itself slows near the black hole's edge, stretched thin by relativistic effects. These hyperspinners likely got their speed from violent origins, perhaps born from the collapse of massive stars that themselves rotated furiously, transferring their angular momentum into the newborn black hole like a cosmic inheritance. Others might have revved up by gorging on gas and stars, their accretion disks acting like cosmic jet engines spinning them faster over millennia. But the true marvel is how their spin changes the merger's aftermath. When two fast-spinning black holes collide, they don't just combine masses, their spins interact like dueling tops, sometimes kicking the merged black hole across space at incredible speeds. Computer simulations show these mergers can launch the resulting black hole at over 3 million miles per hour, a recoil so violent it ejects the object from its host galaxy entirely. That's the universe's version of a slingshot, a gravitational kick strong enough to send a monster hurtling into the cosmic void. These extreme rotations also solve mysteries. By studying spin rates, scientists can trace black holes' histories, whether they grew slowly by steady feeding or violently through repeated mergers. Some rapid spinners might even be ancient relics from the early universe, spinning undisturbed for billions of years before finally encountering a partner. Every chirp LIGO detects carries this spin data, a hidden ledger of the black hole's past written in spacetime's distortions. And as we collect more of these cosmic fingerprints, one thing becomes clear: the universe doesn't just create black holes. It launches them, spinning like tops across the darkness, their rotations whispering secrets about the forces that shaped them. On April 25, 2019, the universe threw another cosmic curveball. Gravitational wave detectors picked up a signal from an event labeled GW190425, a collision between two neutron stars so massive they shouldn't exist as a pair. Together, these ultra-dense stellar corpses weighed in at 3.4 times the mass of our Sun, shattering records for the heaviest binary neutron star system ever observed. The numbers alone are staggering. A typical neutron star, the crushed core left behind when a massive star explodes in a supernova, usually tops out around 2.2 solar masses. But the two objects in GW190425 measured roughly 1.9 and 1.4 solar masses, combining into something that defies conventional astrophysics. This wasn't just a heavyweight pairing, it was a cosmic anomaly that forced scientists to question whether neutron stars could grow larger than previously thought, or if entirely new formation mechanisms were at play. One theory suggests these neutron stars didn't start as equals. Instead, one might have been born heavier, feasting on materials siphoned from a companion star before collapsing into a neutron star itself. Picture a stellar vampire growing unnaturally massive by draining its partner over millions of years. Another, more radical idea proposes that such massive neutron stars could form from the direct collapse of supermassive stars, skipping the traditional supernova explosion entirely. What makes GW190425 truly baffling is what didn't happen next. Unlike the dazzling Kilonova of GW170817, this merger produced no detectable light, no gamma-ray burst, no afterglow, nothing. That silence is just as revealing. It hints that these neutron stars might have merged into a black hole almost instantly, their combined mass too great to form a stable remnant. Or perhaps the collision fired its energy jets in a direction pointed away from Earth, rendering the event invisible to telescopes, but the implications ripple far beyond this single detection. If neutron stars can indeed form in such massive pairs, it reshapes our understanding of stellar life cycles. It suggests there might be hidden pathways, exotic stellar evolutions, or rare cosmic environments that birth these ultra-dense giants in defiance of textbook models. Every detection like this peels back another layer of the universe's rulebook, revealing chapters we didn't know existed. And here's the thrilling part: GW190425 might not be an outlier. As gravitational wave astronomy matures, we could uncover an entire population of overweight neutron stars, rewriting what we thought was possible. For now, this detection stands as a tantalizing clue, a cosmic whisper hinting that when it comes to the universe's most extreme objects, impossible might just be a word we haven't disproven yet. The earliest whispers of creation might still be ringing through the cosmos, not in light, not in sound, but in the faintest tremors of spacetime itself. While most gravitational waves we detect come from violent recent collisions, some theorists believe the universe still carries echoes from its birth, imprinted during the first fraction of a second after the Big Bang. These aren't just ordinary ripples, they're fossil vibrations from cosmic inflation, that brief moment when the entire universe expanded faster than light, stretching quantum fluctuations into cosmic-scale wrinkles in spacetime. Picture the infant universe not as a smooth, featureless void, but as a boiling quantum foam, its fabric seething with microscopic fluctuations. As inflation ballooned space exponentially, those tiny wrinkles were stretched across the cosmos, freezing into primordial gravitational waves that have been traveling undisturbed for 13.8 billion years. Unlike the sharp chirps of black hole mergers, these waves would form a faint, omnidirectional hum, a background hiss of spacetime itself, like static from the universe's earliest moments. Detecting this signal would be the ultimate time machine. It could reveal what happened at energies 1 trillion times higher than any particle collider could reach, offering clues about the unification of all fundamental forces or even the existence of extra dimensions. But there's a catch. After billions of years of cosmic expansion, these waves would have stretched to wavelengths light-years long, far beyond what ground-based detectors like LIGO can sense. That's where future space observatories come in. Projects like the Laser Interferometer Space Antenna, or LISA, plan to float detectors millions of kilometers apart, shielded from Earth's seismic noise. Freed from planetary vibrations, they could tune into these ultra-low-frequency ripples, much like how radio telescopes pluck faint signals from cosmic static. Another approach involves studying the cosmic microwave background, the afterglow of the Big Bang, for telltale swirls imprinted by primordial waves as they interacted with early matter. The hunt is already yielding tantalizing hints. In 2014, the BICEP 2 experiment claimed to have spotted these swirls, only to find their signal muddled by interstellar dust. But the search continues because finding these echoes would do more than confirm inflation. It would open a window into physics at energies we'll never recreate, testing theories like string theory or loop quantum gravity. Imagine hearing the universe's first cries, frozen in spacetime, waiting for us to decode them. If we succeed, it wouldn't just rewrite cosmology textbooks, it would connect us across 13.8 billion years to the very moment reality began. The historic detection of GW 150914, the first gravitational wave ever observed, almost didn't happen. On September 14, 2015, LIGO team was running a blind test, secretly injecting fake signals into their data to keep analysts on their toes. These simulated events, nicknamed blind injections, were routine drills designed to prevent bias, ensuring the team wouldn't jump at shadows when searching for real waves. But that morning, something unexpected happened. As engineers prepared to plant another synthetic signal, the detectors in Louisiana and Washington simultaneously picked up an anomaly so convincing, the team initially assumed it was their test. The signal matched every hallmark of a black hole merger: the signature chirp, the rapid frequency spike, the sudden cutoff. Yet when the engineers checked their logs, they found no record of an injection. Panic and disbelief rippled through the collaboration. Had someone forgotten to document the test, or was this the real thing? The team spent weeks in tense secrecy, triple-checking every possible explanation, from software glitches to deliberate sabotage. One theorist even suggested it might be hackers messing with the system. But as the evidence mounted, the truth became undeniable. They'd captured an actual gravitational wave from a black hole collision 1.3 billion light-years away, right in the middle of a drill. Had the wave arrived just hours earlier, it might have been dismissed as noise. LIGO was still in its engineering run, not yet at full sensitivity, and the detectors were plagued by frequent false alarms. But the universe, it seemed, had impeccable timing. The signal's clarity amidst the chaos made it impossible to ignore, a 1-in-100,000-year fluke that the team later likened to hearing a mouse squeak in a hurricane. The irony wasn't lost on anyone. After decades of work and billions of dollars, the discovery that revolutionized astronomy almost slipped through their fingers because it looked too perfect. And had the team known about the blind injection protocol in advance, they might have hesitated to announce the finding at all. That uncertainty, the very reason for the blind tests, became the ultimate proof of their rigor. When the Nobel Prize was awarded 2 years later, the committee wasn't just honoring a detection. They were celebrating humanity's ability to distinguish cosmic truth from hopeful fiction, even when the universe played the ultimate prank. To catch whispers from colliding black holes, LIGO doesn't just look. It listens with lasers stretched across 4 kilometers of pristine vacuum. Picture 2 beams of light racing down tunnels longer than 3,000 football fields, bouncing between mirrors so perfectly polished they deviate from smoothness by less than a single atom's width. These lasers don't just travel, they dance in flawless synchronization, their light waves canceling each other out to create utter darkness at the detector's output. But when a gravitational wave passes through, it warps space itself, stretching one arm while squeezing the other, altering the laser's paths just enough to disrupt their perfect harmony. The shift is almost unimaginably small, a change in length of 1/10,000th the width of a proton, or about 1 part in a billion trillion. Wrap your mind around that precision for a moment. It's like measuring the distance from Earth to Alpha Centauri, 4.37 light-years, and detecting a variation no thicker than a human hair. Or imagine scaling down the entire solar system to the size of a penny and still being able to track movements smaller than a single grain of sand. LIGO pulls off this feat not once but constantly, filtering out earthquakes, passing trucks, even the distant rumble of ocean waves to isolate the faintest tremors in spacetime. The mirrors at the heart of this system are engineering marvels. Suspended by glass fibers thinner than spider silk, they're isolated from vibrations so completely that their movement is measured in attometers, a scale so small it would take 50,000 attometers to span the diameter of a single atom. Even the lasers themselves are miracles of stability, their frequency so precisely controlled that they drift less than 1 cycle per second over hours of operation. All this sensitivity comes at a price. Stray light, cosmic rays, even the random jiggling of atoms in the mirror's coatings can create false signals. That's why LIGO runs twin detectors across the United States, separated by 3,000 kilometers to rule out local disturbances. When both facilities catch the same ripple milliseconds apart with matching signatures, scientists know they've snagged something real. A distortion that raced through the cosmos at light speed, untouched by planets or dust, to deliver its message across billions of years. What's astonishing isn't just that we built such an instrument, it's that nature gave us waves perfectly suited to detect. Gravitational waves oscillate at frequencies between 30 and several thousand hertz, coincidentally the same range as human hearing. That's why LIGO detections can be translated into audio. The universe's most violent events sing to us in a register we're biologically primed to understand. Every chirp, every thud is spacetime's own language, spoken in wavelengths that against all odds match the scale of our technology and our senses. LIGO isn't just a machine, it's a cosmic ear, tuned to the faintest murmurs of a universe that's been shouting all along. For decades, dark matter has been the universe's most frustrating ghost, an invisible presence shaping galaxies, bending light, and outweighing normal matter 5-to-1, yet stubbornly refusing to reveal its true nature. But gravitational waves might finally crack this cosmic cold case wide open. What if some of the ripples LIGO detects aren't from black holes or neutron stars at all, but from shadowy dark matter objects lurking between the stars? Take primordial black holes, hypothetical relics from the universe's first chaotic moments. Unlike black holes born from collapsing stars, these could be as small as asteroids yet pack the mass of a mountain, forged when dense pockets of the infant universe collapsed under their own gravity. If they exist, they'd be invisible, drifting undetected through galaxies' perfect dark matter candidates. But when two of them collide, they'd unleash gravitational waves with a distinctive high-pitched chirp, far briefer than those from stellar mass black holes. Then there are cosmic strings, theoretical defects in spacetime's fabric, thinner than a proton but stretching across the cosmos. Picture cracks frozen into ice as it forms. These one-dimensional flaws might have formed as the universe cooled after the Big Bang. When strings snap or intersect, they could send out gravitational wave bursts unlike anything we've seen, sharp, isolated spikes in the data with no electromagnetic counterpart. The implications are staggering. If LIGO or future detectors spot these unusual signals, it wouldn't just confirm dark matter's existence, it could reveal its architecture. Are we dealing with a universe threaded with cosmic strings? Is dark matter actually a swarm of ancient black holes left over from creation? Each peculiar wave carries fingerprints that could rewrite cosmology. This search is already underway. Scientists comb through LIGO data for unexpected waveforms, listening for the universe's hidden orchestra beyond the usual instruments. Some even speculate that certain detections like the perplexing GW190814 might already hint at these exotic possibilities. The beauty of gravitational waves is their democracy. They don't care if their source is made of atoms or something stranger. They simply transmit the truth of the collision, undistorted by darkness or distance. Finding dark matter this way would be the ultimate cosmic irony, an invisible substance revealing itself through vibrations in the very fabric it permeates. It's as if the universe left clues in the one language that transcends light and matter, the universal dialect of spacetime itself. Every mysterious signal brings us closer to answering one of science's oldest questions, not by seeing the unseen, but by feeling its footsteps in the dark. Gravitational waves don't just bend spacetime, they race through it at the ultimate speed limit, the speed of light. While a supernova's light might take centuries to pierce through cosmic dust, and radio waves can be delayed by interstellar plasma, gravitational waves barrel through the universe unimpeded, like a bullet cutting through fog. This isn't just a quirk of physics, it's a fundamental difference that changes how we witness cosmic violence. Take the neutron star collision of August 2017. When detectors caught the gravitational waves from GW 170817, telescopes worldwide scrambled to pinpoint the source. The waves arrived first, carrying news of the crash 130 million years ago. But the light, gamma rays, visible flares, X-rays trailed behind by a mere 1.7 seconds. That near-simultaneous arrival wasn't a coincidence. It was proof that gravity and light, though born from the same cataclysm, travel at nearly identical speeds across cosmic distances. What's astounding is how perfectly this matched Einstein's predictions. His equations demanded that gravitational waves, like light, move at exactly 299,792 kilometers per second, no faster, no slower. That 1.7-second delay, it wasn't due to gravity dawdling. The light simply took extra time fighting its way out of the neutron star's wreckage, like a diver struggling to the surface from murky depths. By contrast, the gravitational waves slipped free instantly, unbothered by gas, dust, or magnetic fields. This speed difference isn't just academic, it's revolutionizing how we explore the universe. Imagine a cosmic crime scene. Gravitational waves are the 911 call, alerting us the moment violence erupts, while light is the detective arriving to sift through the aftermath. Without gravity's near-instant signal, we'd miss the most fleeting phenomena like those first seconds of a kilonova, where heavy elements forge in a radioactive inferno. But here's the real kicker. If gravitational waves moved slower than light, their delay would betray secrets about spacetime's hidden structure. Some theories suggest gravity might leak into extra dimensions, subtly slowing its waves. Yet every detection, from black hole mergers to neutron star crashes, shows gravity and light locked in perfect sync. The universe, it seems, plays by Einstein's rules, leaving no wiggle room for hidden dimensions or alternate physics. That neutron star collision wasn't just a fireworks display, it was a cosmic speed test, a verification of relativity written across 100 million light-years. And with every new wave we catch, we're not just listening to the universe's soundtrack, we're clocking its heartbeat, confirming once again that gravity's voice travels as fast as anything can. No delays, no detours, just the pure, unfiltered truth of the cosmos, delivered at light speed. Sometimes the universe's most violent events happen in total silence. On April 26, 2019, gravitational wave detectors caught the signature of a cosmic cataclysm labeled GW 190426, a collision that should have lit up the skies but left astronomers staring into perfect darkness. The signal hinted at a black hole roughly 5 times the mass of our Sun merging with a neutron star, an event expected to unleash a brilliant flash of light as the neutron star was shredded apart. But when telescopes swiveled toward the source, they found nothing, no gamma rays, no afterglow, just the faint echo of a gravitational wave carrying a mystery that still puzzles scientists today. What makes GW 190426 so baffling isn't just the missing light, it's the neutron star's eerie disappearance. Normally, when a black hole tears into a neutron star, the dense stellar corpse puts up a fight. It stretches, warps, and finally ruptures in a spectacular explosion called a tidal disruption event, spraying hot, radioactive debris that glows for days. Yet this time, the neutron star seems to have vanished without a trace, like a pebble dropped into a bottomless well. One theory suggests the black hole might have been too massive or spinning too fast, swallowing the neutron star whole before it could break apart and shine. Another possibility, the neutron star crumpled instantly into a second black hole upon impact, leaving no material behind to ignite a visible firework. But there's a stranger twist. The detectors caught only a single, tentative signal, unlike the clear twin detections that usually confirm an event's reality. Some scientists argue GW1 90426 might not have been a collision at all, but a glitch in the data mimicking a black hole neutron star merger. It's the gravitational wave equivalent of a shadow mistaken for a figure in the dark. Without light or a second detector's confirmation, the truth remains frustratingly out of reach. This cosmic ghost story highlights just how much we still don't understand about these extreme encounters. Most black hole neutron star pairs should form in dynamic environments where stars cluster tightly, like galactic dance floors crowded with partners. But GW1 90426's black hole was unusually lightweight for such a merger, raising questions about where and how these odd couples find each other. Did they meet in a dense stellar nursery, or was their pairing the result of a random cosmic drift? The silence speaks volumes. Every mystery like this forces us to rethink our models of how matter behaves under conditions we can't possibly recreate on Earth. Perhaps neutron stars can be swallowed whole more easily than we thought, or maybe some black holes are better at hiding their meals than others. Until we catch another merger like this one with both gravitational waves and light to compare, GW1 90426 will linger as a tantalizing enigma, a reminder that even the universe's loudest crashes can sometimes happen in perfect darkness. Einstein's theory of general relativity paints spacetime as a smooth, continuous fabric, a stage where massive objects create gentle curves and ripples we call gravity. But peek into the quantum realm, and that elegant fabric frays into something far stranger, a seething, turbulent foam where spacetime itself might flicker in and out of existence on scales a billion trillion times smaller than an atom. This is the quantum foam, a hypothetical structure predicted by theorists trying to unite relativity with quantum mechanics, and gravitational waves might be our best shot at proving it's real. Think of spacetime at this unimaginably tiny scale not as a calm pond, but as a boiling pot of water with bubbles of energy constantly forming and popping. These quantum fluctuations could warp spacetime so violently that even the concept of here and now breaks down. The foam's bubbles would last mere fractions of a second, far too brief and minuscule for any microscope to spot. But if these frothy distortions exist, they'd leave fingerprints on passing gravitational waves, subtle hiccups in the signal that betray spacetime's grainy, chaotic underpinnings. Here's where it gets groundbreaking. Current gravitational wave detectors like LIGO aren't sensitive enough to catch these quantum whispers yet, but future observatories, especially ones in space, could hunt for telltale distortions as waves traverse billions of light years. The longer the journey, the more spacetime's quantum texture would alter the wave's shape, like a smooth radio signal turning staticky after passing through a storm. Some models suggest these waves might even scatter off the foam, creating faint echoes or frequency shifts that defy classical physics. Detecting this wouldn't just confirm quantum foam, it could crack open one of science's hardest problems, a theory of quantum gravity. Relativity rules the cosmos while quantum mechanics governs the subatomic world, but the two refuse to play nice. Black hole singularities, where infinite density meets curved spacetime, expose this rift plainly. If gravitational waves reveal spacetime's quantum nature, they'd hand physicists the missing puzzle piece, a way to see how gravity behaves when space and time themselves are fuzzy and uncertain. Already, theorists are dreaming up what such a discovery might mean. Could quantum foam explain dark energy's acceleration of the universe? Might it hint at extra dimensions curled up at microscopic scales? Every tiny wobble in a gravitational wave could carry answers, etching the secrets of quantum gravity into ripples we've only just learned to measure. For now, it's a tantalizing what if, but in the murmurs of colliding black holes, we might someday hear the universe confess its smallest, loudest truth. Gravity doesn't just create waves, it can twist them too. When gravitational waves pass near a massive galaxy or cluster, their signals don't just sail through untouched. Instead, the galaxy's immense gravity acts like a cosmic lens, bending and distorting the waves in ways that could reveal secrets about the invisible scaffolding of the universe. This phenomenon, called gravitational lensing, is already famous for warping light. Einstein himself predicted how distant galaxies could appear stretched into glowing arcs around closer massive objects. But gravitational waves experience lensing too, with a twist. Unlike light, which gets bent in predictable ways, lensed gravitational waves can arrive as multiple copies of the same event, staggered in time like echoes in a cavern. Imagine hearing the chirp of a black hole collision once, then again seconds or even years later, the same signal split and rerouted by the gravity of an intervening galaxy. These lensed waves aren't just cosmic curiosities, they're tools. By analyzing how the waves distort, scientists could map the distribution of dark matter in the lensing galaxy with precision never before possible. Dark matter doesn't interact with light, but it does warp spacetime, meaning lensed gravitational waves would carry its fingerprint. A single lensed signal might expose clumps of dark matter too diffuse for traditional telescopes to spot, like tracing the outline of a shadow by how it bends a passing breeze. The distortions can get even weirder. In extreme cases, a galaxy might magnify the waves, amplifying faint signals from mergers that would otherwise be too distant to detect. It's as if the universe handed us a gravitational telescope capable of zooming in on collisions from the cosmic dawn. Alternatively, the lens could scramble the wave's shape, smearing its frequency like a record played at the wrong speed. A distortion that, ironically, would help measure the lensing galaxy's mass more accurately than light ever could. While we haven't definitively caught a lensed gravitational wave yet, future detectors like LISA or the Einstein telescope will scour thousands of events for these telltale ripples. Every lensed signal will be a Rosetta Stone, decoding not just the wave's source but the invisible matter it passed through. One day, we might even hear the same black hole merger multiple times, its echoes weaving a narrative not just of the collision, but of the dark cosmos that shaped its journey to us. The universe's most elusive structures could finally betray their presence not by how they look, but by how they bend the whispers of spacetime itself. Some stars die with a bang, but others vanish without a whisper. When massive stars exhaust their fuel, they typically explode in dazzling supernova, scattering their guts across the cosmos. But gravitational waves have revealed a bizarre exception. Some giant stars seem to skip the fireworks entirely, collapsing straight into black holes as if the universe flipped a silent switch. These stealthy disappearances aren't just peculiar, they challenge everything we thought we knew about stellar deaths. The mystery starts with something called the mass gap. Normally, when stars explode, they leave behind neutron stars' incredibly dense remnants no heavier than 2 or 3 solar masses. Anything heavier should theoretically trigger a supernova before collapsing into a black hole. Yet gravitational wave detectors keep catching mergers involving black holes far lighter than expected. Some as small as 5 solar masses, objects that shouldn't exist if supernova always occur. It's like finding a missing step in a well-rehearsed dance, a moment where the music stops but the dancers keep moving. One possible explanation: these stars might be collapsing directly into black holes without the usual explosive finale. Picture a heavyweight star so massive its core implodes under its own gravity, swallowing all evidence before a shockwave can erupt outward. No light, no debris, just a silent, swift transition from star to shadow. Gravitational waves are the only way to spot these covert operations, as their merger signals betray black holes born from quiet collapses. Another theory suggests these oddballs might be the product of stellar mergers, two smaller stars smashing together and skipping the supernova step entirely. Imagine two aging stars locked in a slow spiral, their outer layers stripping away until their cores merge into a single black hole, bypassing the explosive death throes of their solitary cousins. The implications ripple far beyond cataloging cosmic oddities. If silent collapses are common, they could explain why certain supernovas seem to go missing in galaxy surveys. They might even alter how we estimate the universe's black hole population, hinting at legions of dark remnants hiding in plain sight. Every chirp from an unexpectedly light black hole merger isn't just data, it's a clue in an ongoing stellar murder mystery, one where the victims vanish without a trace and gravitational waves are the only witnesses. That Kilonova flash wasn't just a light show. It was a cosmic gold mint operating at full blast. When GW-170817's neutron stars collided, they didn't just shake spacetime, they forged enough heavy elements in seconds to outweigh entire mountains. Picture a stellar alchemy lab where temperatures hit 1,000,000 degrees and pressures crush atoms like grapes, squeezing protons and neutrons into gold, platinum, and uranium nuclei. But here's the staggering part. That single event produced roughly 200 Earth masses of pure gold alone. Now hold up your hand and look at a gold ring. Those atoms didn't come from Earth's crust. They're souvenirs from a neutron star collision older than our solar system. Every ounce of gold humanity has ever mined was born in similar cosmic cataclysms, meaning your jewelry is literally stardust forged in a radioactive crucible. But how many mergers does it take to make a single ring? Let's break it down. One average gold wedding band weighs about 5 grams. Given that GW-170817 produced around 10 octillion grams of gold, that's a 1 followed by 28 zeros, you'd need just one collision like it to create 2 quintillion rings, enough to give every person on Earth 250 million gold rings each. Suddenly, that Kilonova doesn't seem so rare, does it? The math gets wilder when you consider the universe's timeline. Neutron star mergers might happen every 10,000 years in a galaxy like ours, but with billions of galaxies churning out gold over 13.8 billion years, the cosmos has had plenty of time to stockpile precious metals. Statistically, the gold in your jewelry could be a patchwork, a few atoms from a merger 7 billion years ago, mixed with fragments from a crash 3 billion years later, all brewed in different corners of the universe before coalescing in an asteroid that eventually bombarded early Earth. What's mind-blowing isn't just the scale, it's the delivery system. These metals didn't stay trapped near their birth sites. Kilonovae eject material at up to 1/3 light speed, spraying enriched debris across galaxies until it gets swept up in new star systems. That gold could have circled the Milky Way dozens of times before our solar system even formed. Every time you touch gold, you're holding a relic that survived supernova, galactic collisions, and billions of years in deep space just to end up on your finger. So next time someone calls gold precious, remember, it's not just rare, it's the universe's most extravagant recycling program, turning dead stars into heirlooms across billions of years. And gravitational waves, they're the shipping notifications, letting us track when and where the cosmic treasure was forged. When neutron stars collide, they don't just tear apart, they might reveal something far stranger beneath their crushing surfaces. Hidden inside these ultra-dense stellar corpses could be a state of matter so extreme it defies ordinary physics. A strange star, a hypothetical object made not of neutrons, but of free-floating quarks swimming in a primordial soup known as quark-gluon plasma. Picture a neutron star not as a solid, but as a colossal droplet of liquid so dense it breaks the very rules holding atoms together. Here's how it works. Under normal conditions, quarks, the building blocks of protons and neutrons, are forever locked inside particles by an unbreakable force called the strong nuclear interaction. But crush matter hard enough, like inside a neutron star's core, and those bonds might snap, freeing quarks to form an exotic ocean where up, down, and strange quarks mingle freely. This strange matter could be the most stable form of matter in the universe, denser than neutronium and potentially infectious, theorized to convert any normal matter it touches into more strange matter upon contact. Gravitational waves might be our only way to spot these cosmic oddities. When two strange stars merge, their collisions wouldn't just produce the usual chirp followed by silence. Instead, their quark-rich interiors could oscillate like gelatin, sending out prolonged gravitational wave ringing as the newly merged object settles. This signal would carry a distinct fingerprint, a slower decay in the wave's amplitude compared to a regular neutron star merger, betraying the presence of a squishy, fluid-like core instead of a rigid neutron crust. The aftermath could be even wilder. If strange matter is infectious, the collision might trigger a chain reaction, converting the entire merger remnant into one giant strange star in a matter of seconds. Some simulations even suggest these events could eject droplets of strange matter into space, hypothetical strangelets that, if they reached Earth, might rewrite physics textbooks by demonstrating quark matter in its rawest form. So why haven't we found them yet? Strange stars are cosmic doppelgangers, mimicking neutron stars in mass and size but hiding their true nature beneath the surface. Only gravitational waves, sensitive to the subtle differences in how these objects deform and vibrate during collisions, could expose them. Future detectors like the Einstein telescope or Cosmic Explorer might catch the telltale oscillations that set strange stars apart, revealing not just new stellar phenomena, but a state of matter that hasn't existed freely since the universe was a trillionth of a second old. Every neutron star merger we detect could be hiding this secret. The universe might be peppered with these quark-filled enigmas, their existence written in the faint distortions of space-time they leave behind. And if we're lucky, the next gravitational wave signal might carry the echoes of something stranger than we ever imagined, not dead stars, but reborn relics from the dawn of time. The universe isn't silent, it's a roaring concert hall where black holes and neutron stars play the most violent symphony imaginable. Not as soloists, but as a chaotic orchestra, with collisions of every size contributing to a cosmic hum that fills the void. This isn't just background noise, it's the gravitational wave background, a ceaseless chorus of space-time ripples from countless mergers across the cosmos, all overlapping into a whisper so faint we've only just begun to tune in. Picture a crowded auditorium where every instrument plays at once, the deep thud of massive black holes like kettle drums, the sharp clang of neutron stars like cymbals, and the faint plucks of tiny primordial black holes like scattered violin strings. Right now, our detectors hear this as a muddled rumble, like standing outside the concert hall with the door barely cracked. But future observatories like the space-based LISA or the next-generation Einstein telescope won't just hear the noise, they'll distinguish every instrument in the cacophony, isolating individual mergers from the din like picking out a single flute in a full orchestra. What's astonishing is the scale of this symphony. Every few minutes, somewhere in the universe, a pair of black holes or neutron stars collide, each sending out ripples that never truly fade. Over billions of years, these waves have blended into a persistent drone, a fossilized echo of cosmic violence. Some of these signals are ancient, older than Earth itself, while others are fresh, their sources long vanished by the time their waves reach us. Untangling this mess isn't just about cataloging collisions, it's about reconstructing the universe's history. The gravitational wave background holds clues to how black holes grew in the early cosmos, how often neutron stars pair up, even whether exotic objects like cosmic strings or quark stars exist. It's like listening to static on a radio and slowly realizing it's the combined voices of every thunderstorm, every earthquake, every explosion that's ever happened, all whispering their secrets at once. The real magic will come when we can separate the whispers. Imagine identifying a black hole merger from the universe's first billion years, or detecting the faint chirp of a primordial black hole so small it evaporates in a flash. These aren't just discoveries, they're windows into eras before galaxies formed, before stars lit up the dark. The gravitational wave background isn't noise, it's the universe's oldest story, written in vibrations we're finally learning to read. And with each new detector we build, we're not just turning up the volume, we're getting front row seats to a performance that's been playing since time began. Some black hole mergers don't just create chaos, they launch the resulting monster across the cosmos like a cosmic cannonball. Imagine two black holes spiraling toward collision, their orbits tilted at odd angles, their spins misaligned like dueling tops. When they finally merge, the explosion of gravitational waves isn't perfectly symmetrical, it's lopsided, recoiling with such violence that the newborn black hole gets kicked at speeds up to 5 million miles per hour. That's fast enough to cross the entire United States in under 2 seconds, or escape a galaxy's gravitational grip entirely. These rogue black holes don't just drift, they plunge through intergalactic space, leaving their home galaxies behind like discarded rocket stages. Simulations show the aftermath in stunning detail. A supermassive black hole weighing hundreds of suns, hurtling through the void with no stars to anchor it, no gas to feed on, just endless darkness. Some might eventually slow down, captured by another galaxy's gravity billions of years later. Others could wander forever, invisible ghosts in the cosmic night. What's wild is how common these kicks might be. Computer models suggest nearly a third of all merging black holes could experience some form of recoil, though only the most extreme mergers, those with wildly mismatched masses or spins, achieve escape velocity. The record holder, a simulated black hole clocked at nearly 5,000 kilometers per second, or 1.6% the speed of light. At that pace, it wouldn't just leave its galaxy, it could cross the distance to Andromeda in under 5 million years. These ejections aren't just cosmic oddities, they're forensic tools. A kicked black hole dragging leftover gas or stars with it might leave a glowing trail, a cosmic breadcrumb leading back to the violent merger that birthed it. Astronomers have already spotted candidate, orphaned quasars, their supermassive engines apparently flung far from their host galaxies. And if intermediate mass black holes exist, gravitational kicks could explain why they're so hard to find, scattered into the emptiness between galaxies, hiding where no one thought to look. The universe doesn't just create black holes, it punts them. Every asymmetric merger is a potential cannon shot, flinging the densest objects in existence across the cosmos like cosmic shrapnel. And somewhere out there, right now, a runaway black hole could be speeding toward nowhere, carrying the echoes of a collision that reshaped not just space-time, but its own destiny. Black holes are cosmic minimalists, at least according to Einstein. The famous no-hair theorem states that these gravitational monsters shed all complexity when they form, retaining just 3 defining features: mass, spin, and electric charge. Every other detail, what they swallowed, how they formed, even the screams of matter falling in, gets erased, leaving behind objects so simple they're virtually identical except for those 3 numbers. But what if reality isn't that tidy? Gravitational waves are now putting this theorem to the ultimate test, probing whether black holes truly are as bald as Einstein predicted, or if they cling to hidden hair that could rewrite physics. Think of it like trying to describe a person solely by their height, weight, and whether they're left or right-handed. That's essentially all the no-hair theorem allows for black holes. All other characteristics, the equivalent of eye color, fingerprints, or memories, are theoretically obliterated at the event horizon, crushed into irrelevance by the hole's immense gravity. This simplicity makes black holes the ultimate cosmic blank slates, but it also raises a tantalizing question. Does nature truly erase information so completely, or is there more happening beneath the surface? Gravitational waves offer a way to peek behind the curtain. When black holes merge, the resulting object doesn't settle down immediately. It rings like a struck bell, vibrating in specific tones called quasi-normal modes. These vibrations are the black hole's way of shedding distortions, shaking off any irregularities until it conforms to the no-hair theorem's smooth, featureless ideal. By studying the precise frequencies of these ringdowns, scientists can check whether the final black hole matches Einstein's prediction, or if subtle deviations hint at hidden structures. Here's where it gets revolutionary. Some theories suggest quantum effects or exotic physics might leave faint imprints on a black hole's surface, like cosmic tattoos that gravitational waves could reveal. Imagine spotting hairs' subtle deformities in the event horizon that store information about the black hole's history. These could be bumps, wrinkles, or even strange quantum fuzz, all potentially detectable in the way the black hole's ringing distorts passing gravitational waves. Even a tiny deviation from the expected frequencies would be like finding a fingerprint on what was supposed to be a perfectly smooth sphere. The stakes couldn't be higher. If black holes defy the no-hair theorem, it would mean our understanding of gravity is incomplete, perhaps pointing toward quantum gravity, or even holographic universes where information isn't lost but encoded on the horizon's surface. Every new black hole merger detected is another chance to test this, another opportunity to listen for whispers of complexity in what should be nature's simplest objects. And with each chirp and ring down, we're not just hearing black holes collide, we're auditing the universe's accounting system, checking whether it truly erases its ledger or just writes in ink we haven't learned to read yet. Neutron stars aren't the smooth, perfect spheres we often imagine. They're cosmic badlands, riddled with microscopic peaks and valleys that could rewrite our understanding of extreme matter. These deformations, nicknamed mountains, are no gentle slopes. They're thought to be mere centimeters high, but on a neutron star's surface, where gravity is 100 billion times stronger than Earth's, those tiny bumps weigh more than entire mountain ranges. And here's the kicker: as the star spins, these imperfections don't just sit there. They warp spacetime itself, potentially emitting a constant hum of gravitational waves, a whisper so faint our current detectors can't hear it yet. What makes these mountains possible is the neutron star's unimaginably rigid crust. Picture a shell of ultra-dense material 10 billion times stronger than steel, frozen into place by pressures so intense atomic nuclei dissolve into a sea of free neutrons. Even the slightest crack or bulge in this crust could persist for millennia, held up against gravity's relentless pull. Some theories suggest these deformations might form when the star's magnetic field, trillions of times stronger than Earth's, twists the crust like taffy, or when its interior superfluid sloshes against the solid exterior, creating ripples on the surface. But the real magic happens when these mountains move. A neutron star spinning hundreds of times per second would whip its deformations around like a lopsided wheel, generating gravitational waves with a steady, unchanging frequency, a cosmic drone instead of the usual chirps and crashes. Unlike merger signals that fade in seconds, these waves could persist for years, offering a window into the star's structure. Future detectors like the Einstein telescope or Cosmic Explorer might catch this hum and use it to map the star's surface in exquisite detail, turning gravitational waves into the ultimate remote sensing tool. Imagine decoding the topography of an object 20 kilometers wide from thousands of light years away, not by seeing it, but by feeling its subtle tremors in spacetime. The tallest mountains might reveal where the crust is under the most strain, hinting at cracks that could trigger starquakes, violent rearrangements of the surface that release bursts of X-rays. Others could expose the limits of nuclear physics, showing how matter behaves under pressures so extreme even our best theories falter. There's even a chance these deformations could solve a cosmic mystery: why some neutron stars slow down faster than expected. If mountains exist, their gravitational waves would carry energy away from the star, acting like brakes on its spin. That could explain why certain pulsars, rapidly rotating neutron stars, decelerate in ways that defy conventional models. Of course, the wildest possibility is that we're underestimating these mountains entirely. What if some neutron stars have more extreme topography, with crustal floors towering not centimeters but meters high? The gravitational waves from such monstrosities would be louder, easier to detect, and might already be hiding in existing data, waiting for the right algorithm to tease them out. Either way, the hunt is on. Every quiet stretch of gravitational wave data isn't just silence, it's a potential treasure trove of hidden hums, each one a siren song from the most unforgiving landscapes in the universe. And when we finally tune in, we won't just hear dead stars, we'll hear the shape of their scars, the echoes of their battles with gravity itself. The colossal collision behind GW 190521 wasn't just a heavyweight title fight, it was a cosmic whodunit, leaving astronomers scrambling to piece together where such a monstrous merger could have occurred. Most black holes pair up in one of two places: dense star clusters where gravitational traffic jams force close encounters, or the chaotic maelstroms surrounding active galactic nuclei, where supermassive black holes herd smaller ones into lethal orbits. The problem: GW 190521's signal carries clues pointing in both directions, turning its origin story into a gravitational tug-of-war. Star clusters make perfect suspect number one. Picture a globular cluster, a spherical swarm of stars packed so tightly they brush past each other like commuters in a crowded subway. In this gravitational mosh pit, black holes inevitably sink to the center, pairing up through chaotic dances that sometimes end in violent mergers. The math fits. GW 190521's 85 and 66 solar mass black holes align with predictions for repeated mergers in such environments, where black holes grow by swallowing smaller partners like cosmic matryoshka dolls. There's just one hitch: black holes this big should have been ejected long ago by recoil kicks from previous collisions, like pool balls scattering after a break. Enter suspect number two, the fiery disk of an active galactic nucleus. At the heart of many galaxies, supermassive black holes feed on swirling gas and dust, creating an accretion disk hot enough to glow across the universe. Smaller black holes trapped in these disks don't just orbit, they migrate, dragged by friction, until they accumulate in a gravitational slaughterhouse. Here, the extreme density could forge heavyweight pairs like GW 190521's without ejection, while the disk's gas muffles recoil kicks like cosmic quicksand. The smoking gun, the black hole's high masses and nearly identical sizes, a telltale signature of gas-assisted pairing, but the waves themselves hold the most tantalizing clues. If the merger happened in a star cluster, the black hole's spins should tilt randomly like dice tossed onto a table. In an active nucleus, gas alignment would nudge their spins into parallel planes like synchronized tops. GW 190521's signal hints at some spin alignment, but not enough to rule out either scenario. Even the signal's brevity, just 1/10 of a second, plays detective. Shorter waveforms suggest rapid, gas-fueled in-spiral, while longer ones favor the slow gravitational tango of clusters. The answer might lie in the remnants. If future telescopes spot a runaway black hole hurtling away from a star cluster or an active galaxy's nucleus, it could confirm the scene of the crime. Until then, GW 190521 remains a cosmic cold case. its origins locked in the distortions of spacetime it left behind. One thing's certain, wherever it happened, the universe orchestrated a collision so violent it defies our tidy categories, reminding us that the darkest corners of space still hold mysteries no detector can yet unravel. Imagine scouring the ocean floor and finding treasure chests of all sizes except for one weight class that's conspicuously absent. That's exactly the mystery gravitational wave astronomers are facing. After years of listening to black holes collide, a glaring gap has emerged in the cosmic census. Where are all the medium-weight black holes between 45 and 120 solar masses? Here's what makes this gap so puzzling. Black holes come in two well-documented flavors: stellar mass black holes under 45 suns, formed from collapsing stars, and supermassive ones millions of times heavier, lurking in galactic centers. But the middleweight objects that could bridge these extremes are almost entirely missing from our detections. It's as if the universe skipped an entire chapter in black hole evolution. One possibility is these mid-sized monsters are just rare. Stellar physics suggests stars in this mass range might self-destruct too violently in supernova to leave behind black holes, scattering their guts instead of collapsing neatly. Alternatively, they could form differently, not from single dying stars but through repeated mergers in dense star clusters, like cosmic snowballs gathering mass over generations. The problem: our detectors might be missing their quieter collisions. Black holes in this range would produce lower frequency gravitational waves that current observatories like LIGO struggle to catch, like trying to hear a bass drum with a microphone tuned for piccolos. But there's a tantalizing third option. What if these black holes aren't missing at all but hiding in plain sight? Some theorists propose they're masquerading as heavier objects, their true masses distorted by extreme spins or exotic environments. Picture a 50 solar mass black hole spinning so fast its gravitational pull mimics a heavier object's signature. Others suggest they're lurking in binary systems with neutron stars, their mergers drowned out by the neutron star's disruption. The hunt for these cosmic fugitives is heating up. Future detectors like the space-based LISA or ground-based Einstein telescope will scan lower frequencies where mid-sized black holes might sing. If found, they could solve one of astrophysics' biggest riddles: how supermassive black holes grew so quickly in the early universe. These missing middleweights might have been the seeds, building blocks that merged over eons into the giants we see today. Every gap in our data isn't just a blank space, it's a clue. The absence of these black holes challenges our models of stellar death, cosmic evolution, and even gravity itself. And when we finally track them down, they won't just fill a mass gap, they'll rewrite the story of how darkness shapes the cosmos. Right now, our gravitational wave detectors are like stethoscopes pressed to Earth's chest, listening for the faintest heartbeats of colliding black holes. But floating in the silence of space, free from our planet's constant tremors, an even more sensitive ear is being built, one that will tune into the deepest bass notes of the cosmos. Meet LISA, the Laser Interferometer Space Antenna, a revolutionary mission set to launch in the 2030s that will extend our gravitational wave hearing into uncharted territory. Unlike ground-based detectors like LIGO, which catch the high-pitched chirps of stellar mass collisions, LISA will consist of 3 spacecraft flying in a perfect triangular formation, 2.5 million kilometers apart, connected by laser beams so precise they could detect a passing gravitational wave shifting their positions by less than the width of an atom. This enormous scale lets LISA sense ultra-low frequency waves completely invisible to current observatories, the kind produced by mergers between supermassive black holes millions or even billions of times heavier than our Sun. These gargantuan collisions play out in slow motion across years rather than seconds, their gravitational waves oscillating at frequencies measured in millihertz instead of hertz. Picture 2 black holes, each as massive as a small galaxy, waltzing toward doom over centuries before finally merging with a universe-shaking boom. While LIGO hears the frantic last seconds of stellar mass mergers, LISA will catch the entire decades-long crescendo, from the first tentative orbits to the final Earth-shattering collision. The scientific payoff could rewrite astrophysics. Supermassive black hole mergers are thought to sculpt galaxies as they combine, yet we've never directly observed one. LISA might catch pairs spiraling together in the early universe, revealing how these monsters grew so big so fast. It could spot intermediate mass black holes, the elusive missing link between stellar and supermassive varieties, or even detect exotic objects like cosmic strings, hypothetical spacetime defects left over from the Big Bang. But here's the real game changer: LISA won't work alone. By the time it flies, a new generation of ground-based detectors will be online, creating a multi-band gravitational wave network. Imagine tracking a supermassive black hole merger with LISA for years, then catching its final milliseconds with terrestrial telescopes as the waves redshift into their detectable range. This coordinated approach would give us a complete symphony where today we hear only disjointed notes. The mission also solves one of LIGO's biggest limitations: directionality. Ground-based detectors struggle to pinpoint where waves come from, but LISA's spacecraft triangle will act like a galactic GPS, localizing sources to within a single degree on the sky. That precision, combined with the decades-long warning before mergers, will let astronomers train every available telescope on incoming cosmic fireworks. What's astonishing is how quiet LISA workspace needs to be. Each spacecraft must free-fall perfectly, shielded from solar wind and cosmic rays by sophisticated drag-free systems. Their lasers, bouncing between floating test masses inside the craft, will measure distance changes 100 times smaller than LIGO can manage, equivalent to tracking the width of a DNA strand stretched between Earth and Jupiter. We're not just building a better detector, we're constructing a time machine. The supermassive mergers LISA hears will often come from redshifts greater than 20, meaning we'll be witnessing collisions that occurred when the universe was less than 200 million years old. These waves have been traveling since before the first stars finished lighting up the cosmos, carrying untouched information about an era no telescope can peer into directly. When LISA finally launches, it won't just expand our view of the universe, it will redefine it. The same way LIGO opened our ears to stellar crashes, LISA will tune us into the slow, stately dance of cosmic giants, revealing how the largest structures in existence grow and collide. And somewhere in that data might lurk answers to questions we haven't even thought to ask yet, hidden in the vibrations of spacetime itself. For billions of years, the universe has been shouting its secrets in every language it knows: light, particles, and ripples in spacetime. But we only just learned how to listen with more than one ear at a time. Welcome to the multi-messenger era, where gravitational waves don't just whisper alone. They harmonize with beams of light, showers of neutrinos, and cosmic rays to tell the full story of cosmic cataclysms. This isn't just astronomy, it's cosmic detective work, piecing together a puzzle where each messenger brings a unique clue. Take the neutron star collision GW170817. Gravitational waves arrived first with a chirp, gamma rays followed 1.7 seconds later, and days after that, telescopes caught the glowing aftermath in visible light and X-rays. Together, they painted a complete picture no single signal could reveal: the birth site of heavy elements, the physics of ultra-dense matter, even the universe's expansion rate. But the real power lies in what's coming next. Imagine catching a supernova not just by its light, but by the neutrino burst that escapes its core hours before the explosion, and the gravitational waves from the collapsing star. Or tracing a cosmic ray back to its source by combining its path with gravitational wave data, solving a century-old mystery about these high-energy particles. Already, physicists are dreaming of triple coincidences: events where gravitational waves, neutrinos, and light all arrive in sync, like witnesses corroborating a crime from different angles. The potential is staggering. Neutrinos could reveal processes hidden deep inside collapsing stars, while cosmic rays might expose particle accelerators near black holes, all cross-checked by spacetime's vibrations. The universe's most violent events don't play favorites, they broadcast across the full spectrum of physics. A black hole merger might be invisible in light, but its gravitational waves could guide us to spot the faint glow of disturbed gas. A gamma-ray burst jet, if aimed just right, might deliver neutrinos that confirm theories about how these beams pierce through galaxies. And sometimes, like with GW 170817, the collaboration solves riddles we didn't even know to ask, like proving neutron star collisions forge gold, or that gravitational waves and light travel at the same speed across cosmic distances. This synergy is about to explode. New neutrino detectors like IceCube Gen 2 will scan larger volumes of space, while telescopes like the Vera Rubin Observatory will image the entire visible sky nightly, ready to catch any flash linked to a gravitational wave alert. Future missions will even hunt for orphan signals events where one messenger arrives solo, hinting at phenomena still unknown. The ultimate prize, catching something completely unexpected, a signal that defies all current models because we've never had all these tools working in concert before. We're no longer just observers of the cosmos, we're its interpreters, learning to read every dialect it speaks. And with each new multi-messenger event, we're not just solving mysteries, we're discovering how many layers of the universe we've yet to notice. The era of single-channel astronomy is over. The future sounds like a symphony. What happens to a gravitational wave after it's traveled across the universe for longer than stars have existed? These ripples carry the echoes of ancient collisions, but even they may not last forever. As space-time stretches with the accelerating expansion of the cosmos, each wave's energy could gradually dissipate, redshifting into oblivion over timescales that make the age of the universe seem like a blink. Yet there's a haunting possibility that some might survive eternally, becoming the last remaining tombstones for black holes that evaporated eons ago. Here's the paradox at play. Gravitational waves are born from violent events that warp spacetime itself, but they're also prisoners of that same spacetime's evolution. As the universe expands, long wavelength waves from early mergers stretch even further, their peaks and troughs spreading apart until they're barely detectable. It's like drawing a wave on a balloon and then inflating it. The crests grow farther apart, the energy diffuses, and the signal fades into the background hum of the cosmos. Theoretical models suggest that within 1 trillion years, most high-frequency waves from today's detectable mergers will redshift beyond recognition, leaving only the faintest whisper of their existence. But the universe rarely follows tidy predictions. Some supermassive black hole mergers produce waves so low frequency and energetic that even cosmic expansion might not erase them entirely. Imagine two galaxy core monsters colliding. Their gravitational waves could oscillate with periods of years or decades, wavelengths so vast they span solar systems. These might persist like fossil vibrations, carrying their energy forward even as the galaxies that birthed them disintegrate into darkness. In a far future universe where all stars have burned out and black holes have evaporated via Hawking radiation, these waves could be the final evidence that anything ever existed at all. The wildest twist comes from quantum gravity theories. If spacetime has a fundamental graininess at microscopic scales, a foam-like structure theorized to exist, then ancient gravitational waves might eventually scatter off this texture, breaking apart like ocean waves hitting a rocky shore. Alternatively, extra dimensions, if they exist, could siphon off wave energy, leaving our four-dimensional reality devoid of even these space-time echoes. What's profound is the timescale we're contemplating. The last light-emitting objects will vanish in perhaps 100 trillion years, but gravitational waves could outlast them by orders of magnitude. They might carry the memory of our universe's violent youth into an era when nothing else remains, a cosmic archive written not in stone or light, but in the very curvature of existence itself. Every merger we detect today isn't just a momentary signal, it's a message cast into the abyss of deep time, destined to outlive the civilizations that first learned to listen. From the faintest whispers of colliding black holes to the explosive forges where gold is born in neutron star crashes, gravitational waves have shattered our cosmic perspective. These space-time ripples let us hear the universe's soundtrack for the first time, where black holes scream, neutron stars ring like bells, and the very fabric of reality stretches like taffy under the weight of unimaginable forces. Think about the sheer audacity of catching a tremor smaller than a proton, a ripple from an event that happened before multicellular life existed on Earth. Or the revelation that your gold ring contains atoms forged in a cataclysm older than our solar system. Every chirp, every thud has rewritten textbooks, proving Einstein right in ways even he doubted, while exposing cosmic oddities we never predicted, like black holes disappearing without a trace, or neutron stars defying the laws of physics with their impossible weight. But the revolution is just beginning. Future detectors could uncover black holes from the universe's first moments, hear the echoes of quantum foam in spacetime itself, or even stumble upon entirely new classes of objects, strange stars made of pure quark matter, or cosmic strings left over from the Big Bang. Imagine catching the slow-motion merger of two supermassive black holes, each weighing billions of suns, their gravitational waves humming for years like a cosmic didgeridoo. Or decoding the primordial vibrations from inflation, the universe's birth cries frozen in spacetime. The wildest discoveries might still be ahead, hiding in frequencies we can't yet hear, waiting for the next generation of observatories to tune in. What makes gravitational waves so extraordinary isn't just their science, it's their storytelling. They're not just signals, they're time capsules carrying unfiltered narratives from the darkest corners of existence. Every detection peels back another layer of cosmic mystery, reminding us that the universe is far stranger, louder, and more inventive than we ever imagined. So keep listening, because the next ripple in spacetime could reveal something even more incredible. After all, we're just beginning to translate the universe's oldest language. And if history is any guide, the best chapters are still unwritten.